Welcome back, everyone. As your resident professor of biomechanical engineering and, a fellow health tech entrepreneur, I am absolutely thrilled to welcome you to Lesson 3 of this Explainer series. Today, we're doing a deep dive into the strategic and academic side of machine learning for medical device manufacturing. We are officially moving beyond just predicting continuous numbers and stepping into the high-stakes world of binary decisions, because in our field, the right mathematical model can literally protect patient safety.
Okay, let's quickly run through today's syllabus. We're covering the splint quality challenge, why a linear regression fails us, the mathematical sigmoid bridge, logit and cost functions, real data from ISO testing, and finally, clinical validation. We're following the Kolb cycle today to really bridge that gap between our tangible startup problems and deep mathematical theory. Let's jump right in. Part 1, the splint quality challenge.
To ground us in a concrete experience, I want you to picture this. We're stepping onto the manufacturing floor of our health tech startup. We're facing a massive, high-stakes quality control hurdle with our new line of 3D printed orthotics. So I'm posing this critical business and safety question to the room right now. When a device comes off our fused deposition modeling printers, we absolutely have to know, will this specific 3D printed wrist splint pass or fail our structural survival test? There's no middle ground here, folks. Patient safety is on the line. A partial fracture under a load is a total clinical failure. So here's the reality of the situation. We have to strictly classify our output into a binary system. It's either a 1 or a 0. We define class 1 as a pass, meaning the device completely survives structural testing, and class 0 is a fail, meaning it fractures or deforms. Because patient safety depends entirely on these strict quality control predictions, our mathematical model has to confidently categorize every single device into one of those two buckets. No exceptions.
Moving to part 2, why linear regression fails. This brings us to the reflective observation phase of our cycle. We really need to analyze why our standard forecasting tools are, frankly, dangerously inadequate for the specific task. Look, if we try to use standard linear regression, which we mastered in the previous lessons, to predict a pass/fail outcome, we hit a mathematical brick wall. Linear regression plots a straight line that stretches out to infinity, right? So it generates these totally impossible probability values like -0.3 or 1.4. But our binary reality dictates that we need valid probabilities strictly bounded between 0 and 1. An outcome of 1.4 makes absolutely no sense when we're asking for a percentage chance of a splint passing a stress test. So the linear model, it's effectively useless for this medical device classification. Which brings us to part 3, the mathematical sigmoid bridge.
To fix this mess, we have to move into abstract conceptualization, diving into the technical math that actually solves our probability problem. Enter the explicit sigmoid function. The formula is P equals 1 over the quantity 1 plus e to the negative z. This simple, but honestly profound, equation is the elegant mathematical bridge we desperately need. It maps any continuous linear input, which is represented by that z, and compresses it strictly into a valid probability range. No matter how incredibly large or small our input variables get, that denominator ensures the output p never exceeds 1 and never drops below 0. Just think about how beautifully this works when you graph it out. You get this perfect S-shaped curve. On the x-axis, we have our infinite linear input, z. But on the y-axis, we have the probability of passing, p. The curve asymptotically approaches 0 at the bottom and 1 at the top. It's brilliant. We've successfully translated a limitless linear space into a strict, interpretable probability of our splint actually surviving the test.
Section 4, logit and cost functions. But you might be wondering, how do we actually connect our predictor variables, things like material density and wall thickness, to this curve? Well, let's continue our deep dive by exploring how we linearize classification. To make this work, we don't predict probability directly. Instead, we predict the log odds. First, odds are simply the ratio of the probability of passing versus failing, so p over 1 minus p. If our splint has a 75% chance of passing, the odds are 3 to 1. Then, the logit transformation takes the natural log of those odds. And this is the magic of logistic regression right here. In this logarithmic space, the relationship to our variables becomes perfectly linear again. This mathematical space allows our algorithm to learn linear relationships from our manufacturing variables, which are then mapped right back to a probability via that sigmoid curve. Now, we also have to change how the machine actually learns. Back in our linear models, we used mean squared error, or MSE. But MSE treats errors as continuous numeric predictions. For our binary classification, we use log loss, also known as cross entropy. Why? Because log loss heavily penalizes confident but wrong predictions. If our model is 99% confident a splint will pass, but it actually fails and shatters on the floor, log loss applies a massive mathematical penalty. This isn't just some abstract math rule. Penalizing confident but wrong predictions is a vital, absolutely non-negotiable safeguard for patient safety. Quick caveat though, before we get to the real data, we have to play by the rules. To maintain stability and clinical validity, our logistic model strictly requires 3 statistical assumptions. First, independence of observations. One splint's test can't affect another's. Second, linearity in the logit. Our variables must have a straight line relationship with the log odds. And third, the absence of multicollinearity, meaning our predictors shouldn't be too heavily correlated with each other. Otherwise, our coefficients will become totally unstable and impossible to interpret.
Part 5. Real data and ISO tested. Let's get out of the theory and into active experimentation. We're anchoring all this math back to physical manufacturing realities. In the lab, a Class 1 pass strictly requires our device to withstand a static load of exactly 1,173 newtons. We didn't just make that up, it's explicitly mandated by the ISO 22675 standard for an 80-kilogram patient using our specific device. If the splint takes 1,173 newtons of force without permanent deformation, boom, it's a 1. If it fractures, it's a 0.
So what did our logistic regression model actually learn from the physical data? Well, a positive beta coefficient for wall thickness means that as thickness increases, it significantly increases the log odds of a pass. Makes sense, right? But check out the nylon material variable. It yields a massive odds ratio of 2.46. Because nylon has a really high elastic limit of 51 megapascals, choosing nylon over standard plastics literally multiplies the odds of a successful safe production run by nearly 2.5 times.
When you look at a finite element analysis simulation of the safety factor stress distribution, it all clicks. The safe zones, those green and blue areas, show how stress is distributed across the geometry. It visually confirms exactly why nylon's 51 megapascal material properties provided such a strong coefficient of success in our logistic model. The math and the physics are aligning perfectly here.
Finally, Section 6, Clinical Success and Validation.
To wrap up our Kolb cycle today, we need to prove this actually works. We have to examine the diagnostic power and the human impact of our optimized model. We do this by building our ultimate validation metric, the ROC curve. The ROC curve plots sensitivity on the y-axis against 1 minus specificity on the x-axis. According to the research, our logistic classifier achieves an area under the curve, an AUC, of 0.749. That 0.749 is our strict benchmark. It essentially proves that our model has a strong, mathematically validated ability to separate the safe passes from the dangerous failures well before they ever reach a patient's wrist. And here is where it all matters, connecting the math back to the actual patient. The results are just staggering. By using our logistic model to strictly control quality, these 3D printed splints achieve real-world clinical success. The visual analog scale for pain drops drastically, from a 7.34 down to a 3.12. Plus, usability tests show users reporting a 4.9 out of 5 satisfaction level, successfully performing everyday tasks like handwriting and using a computer mouse. It's a total game changer. So I'm going to leave you with this provocative thought as we close out Lesson 3. As health tech innovators, you now hold the mathematical key to binary classification. How will you leverage these exact tools, log loss penalties, sigmoid probability, and odds ratio insights, to engineer the next massive breakthrough in patient care? Think about it. Thank you so much for joining me, and I'll see you in the next explainer.